Okay, welcome. Today we're continuing our tour of various applications of AI. We're going to talk about today and next Monday we're going to talk about robotics. Before I jump in though, were there any questions, I guess, ongoing? I guess there were couple questions on the homework, not really questions, but there's been a bit of discussion on the homework. If we haven't already, we're trying to post some new examples for the, we have already? No. In the process of posting a couple more examples for the variable elimination. I think the big issue is that the queries we give, or a big potential issue, is the queries we give for tests are queries on multiple variables, whereas the one that we give for the test case for the bigger network was just one variable we're querying on. So that might be causing some issues. If you have problems and really think that there's an issue there, let us know, because we're trying to debug all the issues that we can, but people have gotten good the 30 out of 30, so it's solvable. But if there are issues, let us know as we go. The other thing is, I started to do this last week, but I actually will do it today or tomorrow. Put up some information about the poster and the presentation in class for the project. Again, they're pretty brief. You've done similar things before, but we're going to cover that. We'll cover that in a handout today on Piazza. Okay, so are there any questions either about the material, probably not last time, but the time before? You can ask Zach the next time he comes about last times. But are there any questions, sort of general logistics, anything like that? Okay, let's jump into robotics then. So robotics is obviously, like all the things we're talking about now, a very, very broad topic, worthy of much more than a whole school here, much more than a couple lectures. But there are some things that you can kind of pick up if you haven't already seen this kind of stuff in a couple lectures that kind of give you some insight into what a lot of people do in robotics. So these two lectures are going to be broken down largely as follows. Today, we're going to focus on robot kinematics. And kinematics of a robot, as opposed to dynamics of a robot, are really about the geometry of robots, just the configurations that robots can be in, forgetting about the fact that they're actually moving in the world, and that there are things like inertia and momentum. We're going to ignore all that and just think about the actual geometry of these things. And then we're going to talk about motion planning in that context. So motion planning essentially is the question of how do you get robots to accomplish tasks, manipulate objects in the world, and just move around in the world, say without hitting obstacles or without hitting people or things like this. And then next time we're going to talk about dynamics. And dynamics are the case when you now have robots in motion. So when you're no longer just talking about a robot kind of moving statically in the world, but actually moving when you account for things like inertia and momentum, and the fact that you can't necessarily, for all robots, precisely specify the state that's in at every single point. That's what we're going to talk about next time. So now, as with any robot lecture, sort of the fun of teaching robotics is that you can show some cool videos from this. But unfortunately, most of the cool videos people show are sort of in this category here, so they fit better into actually next lecture than this lecture. But in that vein, I want to try to find a couple of these. And actually, this is going to be one that was just made here at CMU. It is very tongue-in-cheek. I think probably a lot of people have seen this before. This is the video of Herb the robot separating an Oreo cookie. So let me try to turn up this volume. It's about 3.5 minutes long, so we'll just go through it. This is one of the, it is a joke, but it's also actually a very cool manipulation task that he's doing.
Exploring robotic platform, I was designed to help people with household duties. I will one day help humans.
Can everyone hear it? Who here has seen this before? By show of hands. Okay. Most everyone, basically.
What they have been learning. Separating Oreo cookies. Apparently that is a big deal for humans.
My name is Srinivasa. I'm a professor at the Robotics Institute at Carnegie Mellon University. We're here at the Personal Robotics Lab. We've been working on her for the past 7 years. It's been both hard and also very fulfilling because finally we're able to do the kinds of tasks that we dreamed of doing the robot like her, separating
So I think this was an ad campaign for Oreo, so it's obviously a little bit tongue-in-cheek. But what actually is, I mean, it is actually pretty impressive there that the level of dexterity that a robot has to employ in order to do a task like that, right? The robot internally, its state, all that it really knows about are the angles of its joints, and then maybe some vision information it has about, so it can somehow see what's going on in the world. But moving from those representations of joints and angles to actual manipulation of the world, that's what we're going to talk about today. We'll talk about kinematics in that respect. I do want to show one more video, though, that this really fits more into the next class. But I'll say why I'm showing it here in a second. This is a robot. This is a new robot. Actually, who here has seen this robot recently from Boston Dynamics? OK, still about half of people. So Boston Dynamics, you've probably seen some of their robots before. This is a company in Boston. Just got bought by Google, actually, I believe, like a lot of companies we talk about here. But they were founded by this guy, Mark Raybert, who actually was a faculty member here, then at MIT. And he really was one of these pioneers in legged locomotion. And so these robots are really amazing in their ability to walk around like animals or like humans. This is an incredibly hard task to do, to build a robot that can not just sort of walk very stiffly like the humanoid robots you might have seen, but actually walk in a very dynamic way, running and jumping and doing all these kind of things. There's a couple pretty impressive slow motion captures here. So there are times when none of the robot's legs are on the ground, times when only a couple are on the ground. And it's really a pretty impressive feat they're able to do. And it does, I believe, here have a little bit of a hiccup. But overall, I think this is one of the fastest, certainly maybe the fastest, or certainly one of the fastest legged robots that there is right now. And the reason why I'm saying this right now, actually, is because Mark is going to be here tomorrow at 12. It says 12 noon. I think it's the 1:30. That was in the email, so I just copied from the email, so that's funny. I guess it's maybe at 12 noon. Anyway, tomorrow at 12, right down the hall, Mark will be talking about these robots. So I encourage everyone here to go check that out. This kind of stuff seems cool. But again, this dynamic stuff is more in the vein of what we're going to talk about next time, though I have to admit, we're not going to get quite that advanced. We're going to be talking about simpler dynamics than that. So let's jump in. As I said, we're going to talk today about robot kinematics and then about motion planning. And these two go nicely together because motion planning, at least how we're going to talk about it, is really going to be about moving robots from essentially one static pose to the next, just in a way that does not collide with obstacles. So, kinematics. Kinematics generally refers to the study of the geometry of robots, as I said. And there are two main tasks that I'm going to talk about here with regard to kinematics. And these are called forward and inverse kinematics. The forward question is, given a configuration of the robot, and when I say configuration, what I mean here is, if we specify a robot's state in terms of the angles of all its joints, right? For a robot like Herb or others, there is certainly some momentum and stuff like this too, but you can also specify the robot state pretty well just by saying what angle all the joints are in. If you specify that, what can you say about the position of the different parts of the robot, right? So where is his hand going to be given the positions of all the angles of all the joints, right? And as you might imagine, this is not that hard a question. This basically boils down to some trigonometry. But doing it kind of in a rigorous way, which we're not going to do here, we're kind of just going to do the simple trigonometry. It still is really important to sort of see the connection between the robot's natural state, which is sort of these joint angles, and the actual position that it then occupies in the world. And then a little more interesting, maybe, though also a lot harder, is the reverse question. And this question says, OK, now if we want to have the robot's end effector at some state, what joint angles do we need to actually do that? The interesting thing here is there actually could be no answer sometimes, right? Sometimes you just can't reach to a certain position in 3D space. There can be one answer sometimes, or there can be multiple answers. Sometimes two, sometimes infinite answers, actually. There can be a lot of different cases here. So these can be tricky questions, but it's really important to know this, too, because a lot of times you want to manipulate things in sort of the world, right? The sort of the world the robot is interacting with. And you need to know how to go from that world to the actual joints of the robot itself. So I think actually a lot of people here I should add are in the Robotics Institute. So this is stuff that's I'm sure going to be very much of a review. But I think maybe next time we'll cover a couple things that might be unseen before. Anyway, let's talk about this. We're going to talk first about forward kinematics, and we're going to talk about inverse kinematics. So the forward kinematics problem, as you might imagine, is just a matter of really trigonometry. The running example throughout this this part of the lecture, at least, is going to be this example here of a two-link planar robot. So this robot's the one that everyone uses to sort of learn robotics with and learn simple geometry with. The idea is it has two links here. The first one has length L1, the second one has length L2, and then its end has some hand or something like that. But we're not going to actually even worry about the hand. We're just going to try to position that end effector. This is the hand, call it an end effector, at a certain position in space. So the robot's configuration here is really described by four different things, but then those imply a set of two other things. The first are what I'm calling robot parameters, though it's second in this list. The first, and this basically describes the length of these two things, right? Those, at least in this robot, are going to remain fixed. We're not going to change the lengths of the links here. We're going to keep two fixed length links. What does change are these variables theta 1 and theta 2. And these are the joint angles of the robot. I will refer to the joint angles of the robot, and they go by a lot of names, but basically the space of all allowable joint angles is sometimes called the configuration space of a robot, or sometimes just the joint space of a robot. These four things then imply, again, as you can probably imagine just by simple geometry, they will imply what the position of the end effector has to be. And this position in Cartesian space now is just an xy coordinate in what I'll call the task space. And it's called task space usually because when you think about doing some task with the robot and you're grabbing something or something like that, you think about performing a task not in the space of the robot's joints, but in the space of the actual world you're trying to manipulate. And really, as I said before, kinematics is really just how we move back and forth between these two representations, the task space representation and the joint space representation. So let's just go through how you actually do this. The first case, as I said, is probably going to be pretty simple. But basically, you have your joint space. And in joint space, the two things can really span any angle. We're not going to talk about there being any constraints on our angles here. We're just going to talk about them being able to revolve as many times as we want, not collide with anything. Just you can rotate as much as you want. And so in that case, the space of allowable joints really ranges from -pi to pi in both directions. But really, this could go on forever because the only reason I'm stopping here is because this point here is the same as this point here. So you're allowed kind of complete free movement in the joint space of the robot in this simple example. But then in the task space, you're going to be much more limited, right? Because in the task space, no matter how you position the robot's joints, you're never going to be able to reach beyond, it's kind of unfortunately a little bit hard to see in this picture now, but you can never reach beyond this radius, which is the this sort of circle here in task space, where the radius of the circle is the two lengths of the robot summed together, right? Because if you had this robot, it can never reach beyond the space that's sort of spanned by these two links here. And as I said, forward kinematics is how you go from joint space to task space, and inverse kinematics would be how we go from this space to that space. And we'll see how this sort of inability to reach every spot in the task space will relate to our solution to the inverse kinematics problem. But first, let's just talk about forward kinematics. The forward kinematics, as you can imagine, is really pretty simple. I'll just draw this here again because we're going to keep referring to things like this. But basically, you have two parameters, theta 1 and theta 2. Or sorry, two joint angles, theta 1 and theta 2, two parameters, the L1 and L2. And you just apply trigonometry to figure out where everything is, right? So to figure out this point here, the elbow of the robot, that position would be x0 would equal L1 times the cosine of theta 1. The y position of this guy here, this elbow here is x0, y0. It's just L1 times the cosine of this, and then L1 times the sine of that. Then if you want to find the position of this next guy, which is the end effector, you just take this and you add the next sort of sines and cosines in our chain. So the x position, for example, would just be this plus this. This term here would just be the x-coordinate if now your new origin is at x0 and y0. Your new angle is actually going to be the sum of these two angles because you actually rotate. You already have the rotation of this one, and then you rotate more based on that one. And so your final position is just going to be the elbow position plus whatever you add from the second link. And similarly, for the y-coordinate, you get this. Okay, so very simple. This is sort of high school trigonometry, but kind of makes things good to have them be a little bit concrete, I suppose. And now for simplicity, here and sometimes later on, I'll occasionally write this as L1 times C1. So here, C1 will always be the cosine of theta 1, and something like C12 would be the cosine of theta 1 plus theta 2. And similarly for these S terms, these are the sines of theta 1 and the sine of theta 1 plus theta 2. OK, so now it's a simple bit of math here. But what we've been able to answer really is this question of, if I configure the robot in a certain way, namely give it certain joint angles, here is where the robot's hand will end up. Right? So the opposite problem is harder. Right? The opposite problem says, if I want the robot's end effector to be here in 2D space, how should I position the joint angles to get there? And this is hard because, as you might imagine, there are lots of cases here. Right? So first of all, there could be an infinite number of solutions. For the 2D case with two joints and two positions in 2D space, that happens only in one place. It happens only when you want the robot's end effector to be at the origin. Right? Because if you want it to be at the origin, so we have this robot. We want its end effector here to be there. How do we go about doing that, actually? What should the settings of the joints be? There's an infinite number, so a lot of things are right, but not everything. How should we do that? Yeah. Right, so theta 2 has to be pi equal to pi. Basically, you just rotate this all the way to here. So the robot's first one goes like that. Second one just comes back across it. And then theta 1 can be anything. And theta 2 is equal to pi. I guess, all right, yeah. So I guess here I am assuming that the lengths are the same for this being infinite. Good point. Otherwise, there are not infinite solutions there. So these also depend a little bit on the parameters of the robot too. But in this case, if the parameters have these things being the same, you would have infinite solutions there, but really only there. Actually, it's kind of a unique case for, again, a robot with two joints and positioning in 2D space. You might have two solutions sometimes, and exactly two. And that is just the case because the robot starts here. We want the end effector to be right there. You could, of course, either have it this way or this way, right? You can have the elbow up or elbow down configuration. Those are both valid solutions to this problem. And in fact, most, I guess, in some sense, most points in 2D space will have two solutions. because you will in fact be able to, well, most places they can reach will have these solutions because you will be able to either have the elbow up or the elbow down. You can also have one solution. So if you're exactly on the circle described by L1, L2, then theta 2 has to be 0, has to be fully extended, and you only have one solution. And finally, if you're beyond the length that the robot can reach, you have 0 solutions. Now, in general, inverse kinematics involve the solution of nonlinear equations, right? These are nonlinear equations. They have sines and cosines. And in general, you cannot solve those. If you have an arbitrarily complex robot, you'll come to situations where you cannot actually solve the inverse kinematics function. However, because it's so useful to be able to do this, people have designed robots such that this is solvable, actually. And for a simple case like this two-link manipulator, you definitely can solve them. And you basically do it by playing around with inverse trigonometry a little bit. And it's somewhat of a, there are sort of methodological ways to do it, but there also is a kind of a lot of art to do it as simple as possible. For this case, it's pretty simple, but even you'll see in this case, it kind of is a little bit annoying to go through this math. So it's kind of a pain still, even in the simple case of a two-link manipulator, let alone when you have a 3D robot that can position both the orientation and position of its end effector. This becomes a very complex task. The code's out there, it's written, you can just do it, but it's a pain to derive. And if you had to derive it, it would take, from scratch, it would take a long time. So let's do it for this simple case, though, just to show you how this works. And if it seems arbitrary, you're probably a little bit right. It is a little bit arbitrary how we're going to do certain things and which angles we're going to use where, but this is what works for this robot. So the first thing we're going to do is note that you can think about the end effector position being some function of the joint positions. And this equation here is always fairly well defined, right? Because this is the forward kinematics function. That one, there's no problem. It's nonlinear, certainly. There's trigonometric functions there, but it's always well defined. There's no set of joint angles where you don't have a corresponding position in 3D space. That way you always have it. So we can define the forward kinematics function this way, and then we can treat inverse kinematics as the optimization problem of minimizing over our joint angles this forward function minus some desired position for the end effector, and say we'll have the 2 norms squared here. Now, if you can actually achieve this position, this will always have optimal solution 0 when this is actually at the position you want it to be at. But, for example, if you had only 2 joints here, and you're trying to control a point in 3D space, that's not going to be possible. So that would be one case where you would be underdetermined. You cannot find, you know, if you have a planar robot, you can never reach out into the 3rd dimension. There are also cases, though, where you might actually have more joints than you have positions in you have more joints than you have degrees of freedom in 3D space. And the reason for this is that with this planar robot, or this planar robot here, you are very constrained in that if you want to reach a certain point in 2D space, you have to have the robot in a certain configuration, right? It has to always be right, sort of reaching right at a certain point. And all its elbow and everything else has to either, I mean, it could be either this way or this way, but it has to be one of those two. And that can be a problem if you have things like obstacles in your environment, right? Just think about sort of you reaching for something. We are very nicely able to kind of move a little bit our elbow where we want to, while still having some freedom about where we keep our hand, right? I can sort of move, also have rotational freedom, this or sort of freedom to move my legs, but it can be a big advantage for manipulation tasks to have extra degrees of freedom that you can use to actually avoid other things in your environment while still keeping your end effector at a desired location. And so for this reason, there actually are cases where you have more joint angles than you have points in space that you need to control. And in this case, you actually need some sort of optimization or some similar kind of formulation such that you can say, of all these positions that I could be in, here is the best one. And then, of course, this is not a convex problem. This is going to have cosine and sine terms in there, so it's not going to be easily solvable. It's not going to be convex. But we can solve it with gradient descent or methods like this. These can't have local optima, so even if a solution exists, they are not guaranteed to always find it. But in a lot of cases, especially if you are doing things like motion planning, where you start at a reasonably good location, these work pretty well. And so there are a lot of cases where you actually want to do something like this and solve this as an optimization problem instead of solving it analytically. Now, the last thing I'm going to say about kinematics in general is this term called the Jacobian. This term will come up a little bit more in dynamics. But the Jacobian is here just the partial derivatives of the position of the end effector with respect to the angles of the robot. All right, so this just, we have a function that manipulates between these two. Essentially, x and y are given as this function here. And j is just going to be the Jacobian of this function. Actually, Jacobian generally refers to any sort of matrix of derivatives like this. You can actually refer to that when we talk about calculus. The Jacobian would be sort of this matrix for any function. But in robotics, it almost always will refer to the actual Jacobian of the mapping from configuration space to task space. So in this case, these first two entries here would be the partial derivatives of the x-coordinate with respect to the first and second joint. And similarly, the partial derivatives with respect to the y-coordinate of the first and second joint. These are pretty easy to actually compute. Again, they will have sines and cosines in them because this is all trigonometry. You're not going to ever lose that because if you take the derivative of a sine, it's the cosine. But they're pretty simple to compute, really. So we'll just compute one here. So say this guy here. This term here is the derivative of the x-coordinate with respect to theta 1. So x, remember, equals L1, I'll just write it out, cosine theta 1 plus L2 cosine theta 1 plus theta 2. Right, so taking the derivative with respect to theta 1, all you'll have is this will become a negative sign, so you'll have L1, so the derivative of this thing with respect to theta 1 would equal negative L1 times the sine, this thing, minus L2 times the sine of theta 1 plus theta 2. And similarly for all these other terms. Now, there are a lot of uses for the Jacobian. One nice thing here is that the Jacobian tells you, I mean, what it's saying in some sense is here's our configuration, here's our end effector. What these are by definition is just to say if I move one of the joint angles a little bit, how will that move my actual end effector position here? And similarly, if I look at kind of the directions that I can move my end effector, how are those affected by a little change in the angles here? And one thing you can use this for, amongst many other things, but one thing it's going to be used for is kind of a smooth version of these cases we talked about before, where you may sometimes have one solution, you may have a lot of solutions to the inverse kinematics problem, et cetera. What you'll find is that sort of by pure inverse kinematics, what we found is that if you pick a point, x, y, that's right on the boundary of radius L1 plus L2, that will have exactly one solution to your inverse kinematics, whereas if you move even a tiny little bit in, it'll have two solutions, right? Because you could now either be crooked a little bit this way or a little bit that way. What you'll find in the Jacobian for this case is that the Jacobian at this point, when you're fully extended, will actually be singular. It will have an eigenvalue that's equal to 0. And the reason is, when you're fully extended here, there is nothing you can do to move the end effector in that direction or this direction, right? there's sort of no small. I won't say this one. Just say this one. The other one is a little bit odd. You have to just sort of do two different manipulations. But basically, nothing you can do will actually move the manipulator in that direction, right? What that corresponds to is saying that there is no set of theta 1 and theta 2 where a small change of theta 1 and theta 2 could lead to moving in this direction, right? And because of that, this Jacobian, by sort of definition, but also if you look at it mathematically, has to be singular. It has to have an eigenvalue equal to 0. But what's nice here is that if you move a little bit in, the Jacobian will be almost singular, telling you essentially you can't move very far in that direction, or rather it would take a very big change in your inputs to get any sort of change in that direction. And that can encode kind of this sort of smooth. What that does is that kind of specifies this sort of smooth continuum of having one solution when you're fully extended to having many solutions when you're sort of right in the kind of normal manipulation area here. The Jacobian will capture sort of how constrained you are by the eigenvalues of this matrix. Another use for it is that it also can be used to relate velocities in joint space with velocities in task space. And this is just actually simple chain rule here. If you actually have, instead of just a fixed set of joint angles, if you actually have a set of joint angles that vary over time, the Jacobian is precisely that term that relates the velocities of the end effector to the velocities of your joints. And I probably actually should have written J of t there, just to emphasize that, because the Jacobian, remember, it has the sines and cosines in the Jacobian, right? So if you move a little bit, you will have a different Jacobian. It's not a constant matrix. This is a matrix that depends on the actual angles here, just giving you kind of the instantaneous changes for that set of angles and as a first order approximation. But at a first order approximation, what this is telling you is that this, the instantaneous velocities right now will relate to the instantaneous velocities in joint angles based on the instantaneous Jacobian. And that just follows by the chain rule. Essentially, if you differentiate this, xt with respect to t, you'd get a term with xt partial x partial theta, and then partial x partial theta 2. And this is just the chain rule for the multivariate case. So that follows pretty much by definition almost. So we'll come back to the Jacobian a little bit, maybe kind of non-rigorously, but a little bit in the next lecture. But you should at least know what Jacobian is in the context of robotics. As I said, in general, it is just a derivative or a multivariate extension of a derivative. But in robotics, it always refers to this derivative of the task space variables with respect to the configuration space variables. All right, are there any questions about anything so far? How many people have taken robotics class already and sort of already know all this stuff? So half, a little more than half? OK. Next lecture might be a little more interesting, but this is still fun, right, to go through all this? OK. The last thing I'll say here is that general manipulators are quite a bit more complex than this. So in general, you don't just have a 2D system, right? We like robots to actually operate in 3D space. And not only do you need a robot that can reach anywhere in 3D space if you want to manipulate objects in 3D space, you also typically want to be able to configure the orientation of the end effector to be any way it wants, right? So when Herb was trying to grasp the cookie, it couldn't just sort of put its hand anywhere where the cookie was. It actually had to place its hand such that when it grasped right there, it would exactly grasp the cookie. And so basically because of that, you need however many degrees of freedom you want in the world, you need at least that many joints in your robot. So typically, if you want to have a full control over 3D position and rotation in 3D can also be parameterized by 3 different quantities, you need at least 6 joints in your robot. Actually, 7 is more common. Again, to account for the fact that you want to have some extra degrees of freedom to be able to do things like move your elbow while grasping the same spot. These are kind of trickier in this case, certainly. But forward kinematics, in some sense, it's still easy to solve. The notation is kind of gross. You'll see a lot of these matrices with like these R matrices that have superscripts and subscripts and all sorts of funny things like this. But really, it's just pretty much trigonometry here and some matrix math to actually go from joint angles to position in 3D space. Inverse kinematics is much harder, to the point where actually sometimes actually is not solvable. You have to just do something based on optimization, or doing kind of partial inverse kinematics and other parts being, having an optimization problem for some parts of it and not for other parts. These kind of things which you have to do when you have very complex systems interacting in 3D space. OK, that's all we're going to talk about for kinematics. I want to jump out to motion planning. Motion planning, as we're going to talk about it, deals with the question of, what if I throw some obstacles into my task space, usually, and I wanted to be able to move the robot to get around those things? Now, objects do typically lie in task space, right? We don't usually think, maybe things like joint limits would be naturally encoded in configuration space. For the most part, obstacles in the real world are going to have a 3D position, or 2D position in our planar case. But the reality is, we don't really want to work. We can sometimes, but sometimes, for a lot of reasons, we don't always want to work in the task space of the robot. There are these issues like having 2 solutions, right? So if we want to, say, reach to one spot, and we have 2 solutions, which one do we choose? This is not a trivial issue either, because sometimes one of them could be colliding and the other one isn't. And sometimes if you just plan in task space, you can go through places where there's always a solution, but you can't actually attain it because you have to instantaneously switch between the elbow up and elbow down configuration. So for a lot of reasons, we'd rather not deal with planning over time in task space. We want to do that in the configuration space of the robot, just plan the actual joint angles. Because we have to do that at some point anyway. It's what the robot actually sees. So let's just do the planning in that space originally. So what we need to do instead is figure out what poses, if you have a situation like this, where you have a T-link manipulator and an obstacle here, we can ask the question, what states of this system collide with that obstacle and which ones don't? The ones that are not colliding with the obstacle are called the robot's free space. Sometimes called the free configuration space, but free space is just kind of the more common term. This is not, while this is an easy problem to ask in some sense, describing these things analytically is not always very easy. It's even harder sometimes than doing inverse kinematics. So look at this simple case. Here's the case where we have a T-link manipulator. Each length here is actually of the same size. They're both length 1. And I want to ask, there's an obstacle here placed at 1. Sorry, this should be 1, 1. Just 1, 1. With a radius of 0.5. Does anyone have any idea what the configuration spaces, or what the free space will look like for this? Yeah. Do you have an idea what it looked like? No, OK. So what I'm asking here is, if you were to plot now all possible poses of the robot. So this would go, say, from negative pi to pi, and negative pi this way to pi, these being 0. Some of this space here will be colliding with that obstacle, and some of it won't. Right? Do you have any idea what it's going to look like? I wouldn't have. I had to just plot it, I'll say. Maybe people know, yes, do you have a better intuition what it would look like?
So are we assuming that that's...
Each one has length, length 1.
What's the current theta 1 in that picture?
This current theta 1 is pi over 2, and the current theta 2 is pi over 4.
Okay. So in between 0 and pi over 2, there's a region that theta 1 cannot be.
Right. Because anywhere there, it would hit that obstacle, right?
And then for certain theta 1 values, there are also theta 2 values that would hit that.
Right. So here's what it looks like. And you can describe this analytically, but I didn't do that here. It's kind of a pain. So what I did was just generate a bunch of samples in this space, check if they're colliding or not, and then plot it either as red or blue. It's going to be a common theme, actually. That's what we're going to do to plan, too. We're typically not going to try to enumerate these manifolds analytically. What we're going to do is we're actually just going to sample from the space and check if it collides or not, because that's much easier to do than trying to delineate the actual curvature of these regions. Here's what it looks like. So you definitely can get this thing right, because that's kind of like the case where there's nothing here at all, right? If this swings in this region, you know it'll hit it, and so that's no good. But this shape here is kind of it's intuitive once you see it, but it's not at all intuitive immediately. So basically what this corresponds to is if you're a little bit below the obstacle, that would be this region here, then in that case, if you have your link this way, you're okay as long as you don't move your theta 2 too much this way. If you move your theta 2 too much this way, then you're in trouble. But these little precise regions here, I mean, these little non-convex regions here, they're really not intuitive at all. Why it looks like this. It's just the math here that makes it look like this. Similarly, if you make a small change, like make the radius 0.4 instead of 0.5, what would it look like? What would it be now? Yeah, so it actually looks like this. And the 0.4 and 0.5 here is a big difference, because 0.4, this point here is at, ignoring this, is at 1, 1. So the distance from this, the origin to this, is the square root of 2. So it's 1.14. So if this radius is bigger than 1.41. If this radius here is bigger than 0.41, there's always a region where it's going to collide, but if it isn't, then there isn't, and it can actually pass through that. So there are all these kind of points here, right, where there's these sort of transitions between something that can always collide in a certain region and not collide in a certain region, and it's very non-intuitive. And this is about as simple as you could get. It's a 2-link robot with one circular obstacle. Even when you have square obstacles, this becomes a lot nastier. So we typically probably then don't want to try to do manipulations at the level of the precise geometric manifolds we're talking about here. And this motivates a lot of work in what we'll talk about the rest of this lecture, which are called sample-based planning techniques. So sample-based planning. Suppose we did want to move from here to here. Or actually, maybe, because that's kind of easy, maybe like from here to here. How would you do that? It's kind of obvious here, right? Because here you can say, okay, so if I'm here, that's my current configuration, and I want to move to this spot over here, well, I just kind of go like that, because we know exactly what this space looks like. The problem is, we only can know what it looks like because I can sample enough in this space to sort of get some idea of what it looks like. In general, as I said before, there's no good description of these regions here, and we can't really delineate them. All we can do is say, am I in this pose, am I colliding or not? So we need other ways of actually doing this. And sample-based planning is a very nice way of doing this. The basic idea is even though we cannot quickly delineate the precise structure of these manifolds, what we can do is very quickly check if we're colliding or not, right? And I should also say that's not that quick. Collision detection is still not an instantaneous problem, especially when you have complicated bodies and sort of complicated non-convex regions you have to try to collide with each other. It's not trivial, but it can at least be done, right? It seems like a concrete question at least. Right here, am I colliding or not with this obstacle? And this is motivated a class of algorithms that will essentially, what they do is they sample random points in the space. And when I say random, they are random to a certain extent, but they're also kind of what differentiates different algorithms is precisely how they pick those points. We're going to sample some set of points in the underlying configuration space and try to build paths in that configuration space that don't hit obstacles. So let me give you an illustration of what this looks like. And the kind of classical now, I guess it's probably old enough that I call it a classical algorithm for doing this, is a method called probabilistic roadmaps. And now people actually differentiate between probabilistic roadmaps and some other things we're going to talk about here later. But really, I consider them all sort of classes of probabilistic roadmaps. If you're doing sampling in configuration space, trying to hit obstacles, that is a PRM to a certain degree. The precise details of how you sample will certainly change your algorithm, but they're still kind of conceptually a very similar approach. So let me, though, show how kind of the simplest algorithm here would work. So what I'm showing now is a plot of configuration space of the robot. It's hypothetical, but what we're saying here is we have two joints to this robot, theta 1 and theta 2, and everything in the pink here is colliding. There's some funky shaped obstacles in our environment such that we can only be in this blue space. This looks really crazy, but isn't actually that crazy. I mean, you could easily have things like this, so it's actually not that hard to throw in a bunch of things together and joint limits that, as a whole, make it look kind of like this. But again, this is just a cartoon here. The simple approach, then, is just the following. We're going to take our space here and draw a bunch of random samples. And we'll just think about sampling uniformly. So we're just going to draw uniform random samples all over our configuration space. Whether they're colliding or not, we don't pay attention. Right? And then we get a set of points like this. Then, naturally, we don't want to have points here that are colliding, so we're going to remove all the points from these samples that are colliding. Then, we look at each point and consider all its neighbors, where neighbors is defined somehow. I mean, whether or not you want this to be a neighbor or it's not close enough to be a neighbor, don't worry about that. But we're going to consider all the neighbors, in some sense, of every vertex that we sampled here. We look at the edges between these two vertices, and we throw them out if the edge itself goes through an obstacle. Right, then we do this for all the nodes, and we get something like this. Note that not every sort of passage here is actually being covered, right? We got points here, but just to bad luck, we didn't sample enough points to get good coverage down here. And so there's actually no path that will go, say, around this way in this current roadmap. So now we build, connect the nodes this way to form a graph. Hopefully it is a graph and not, or rather, hopefully the graph is connected and not a set of disjoint graphs. But we do this, and then now, if we have 2 points in configuration space that we want to connect, all we do is we take these 2 points, we connect them up to the existing graph, and then we plan a path through that graph using whatever planner we want, right? This can be all the various graph planning algorithms or search algorithms that we learned throughout this course. Okay, so conceptually, that's pretty simple, right? The big idea really was just random sampling. forming these edges in the configuration space between two random samples. And then when you get a new set of query points, you just connect it to the graph and go from there. And this is actually a surprisingly effective technique in a lot of cases, with some caveats. Because there are some things that are very hard for this to do right, but this is actually not at all a bad algorithm. I think in initial motion in sort of historically in motion planning, for a long time people didn't sample randomly. They would just sample kind of in a fixed deterministic fashion. And what they found was essentially this randomness can actually really help you here. Just having a little bit of randomness makes you not have to worry about sort of is your precise strategy for sampling. Why did that happen? I turned it on just before lecture started. So basically what happened was these methods had been around for a long time, but sort of the injection of randomness, and in particular, the creation of new ways of actually doing random sampling really was a big boon to these kind of methods and really made kind of a lot of progress. Plus just, of course, more computational power, right? We have much more computational power than we had 20 years ago when these things sort of probabilistic motion planning first got underway. And now we can be sort of much more powerful, generate many more random samples, do much more collision detection, et cetera, to really get much better plans through these kind of spaces. Has to cool down now, so actually maybe I'll just pause and see if are there any questions about this. I'm pointing here, but it's not. Keep going, it's fine. Are there any questions about this? I have like 30 seconds left before we can start again. So what could go wrong here? Yeah, this question?
So when you pick the neighbors with the edges, you don't pick all the neighbors, right?
Right.
Which one, how do you set?
Yeah, that's a good question. And I'm not answering that intentionally. I'm just saying in nearest neighbors, where nearest neighbors say is within some ball. Is the simplest way of doing it. You can also pick ones that essentially that create a planar graph where we never cross edges when you build the whole thing. You can do things like that, but really it's sort of immaterial to a certain extent here. You just pick some neighbors and you connect them. The question, of course, is things like what could go wrong here, and a lot of things can go wrong. Yeah, it could be not connected. That's one thing that could go wrong. What else could go wrong?
Some of the motion in the task space might require large or.
Oh yeah, so actually I'm doing this all in configuration space, right? So that sort of the trickiness about going from task space to configuration space is somewhat avoided if you do all your planning in configuration space. Then you have to worry about things like, am I right at the boundary of my reachable set so that I can't, so I need a lot of force to maintain the position there. But there are some tricky parts here. So one thing I kind of just leapt over here is that I said, okay, we're going to form these paths and we're going to throw out all the ones that are colliding. But that's not an easy problem, right? What we can do, remember, the algorithm does not know the underlying geometry here. It does not know what this looks like. It just has points. To ask, is a point being colliding, that's kind of a well-defined thing, right? An entire line, a trajectory being colliding, that's actually trickier. It's not obvious how you go from one to the other. One thing you can do, for example, is just check a lot of points along each line and see if all of them are non-colliding. But then, of course, you have cases like this, right, where you basically have a very skinny obstacle, and you check your uniform points, and it looks great, and you're actually just punching through an obstacle. This is not a trivial. This is not sort of this does happen in practice, especially when we start doing things like optimization with these things. They're very likely to say, okay, I don't want to be in this obstacle, but being on either side of it, that's fine. And then I'll just, we won't worry about going through it. So what this sort of boils down to is we need to ensure that however fine we discretize, that scale there is smaller than the size of any obstacle, is what it boils down to. We have to discretize to a scale finer than our thinnest obstacle. And you can do this by kind of adding like a safety margin to obstacles so that we don't, we actually, even if an obstacle is just a plane, we actually think of it like a box. But there are other problems too. For example, there can be this problem of bottlenecks and corridors in the space. So if we have a lot of things like this, sort of narrow passageways, where we have to kind of get lucky and randomly sample a lot of points in here before we get a good path through it, that can be really hard, right? Because we have to kind of get enough samples that we're actually able to form sort of the narrow passages through these spaces. There's also the problem of random sampling in a hypercube. 2 dimensions, that's no problem. Maybe 5, okay. 6, maybe. 10, no. You cannot densely cover a 10-dimensional hypercube with random samples. You're going to take forever. A 10-dimensional robot is not that big. If a humanoid robot, there's 10 dimensions, no problem. Touching more on what you said before, how do you construct the graph? How do you pick those nearest neighbors? If you want to pick every possible pair, right, that would be just take far too much time. How do you pick them? How do you know when to connect things in a loop or not or whatever? And then what about the dynamics? What if you do have some systems that maybe can't immediately move from one state to another state? More on this next time. We're not going to worry about this just yet. But these points are sort of real issues here. And so to address them, I'm going to present one algorithm that people have used, which is called a rapidly exploring random tree. People often actually describe these as an alternative to PRMs. I am framing them here as a way of generating samples for what is effectively the same thing as a PRM. But what this boils down to is this is a way of generating sample points and a graph that you can use as a probabilistic roadmap. Who here has seen RRTs before? OK, great. So why would you use this? Well, practically, it scales slightly better to higher dimensions than random uniform sampling. It actually, the sampling that you get from an RRT tends to essentially sample nicely in, well, actually I won't say technical stuff here, but basically it gets sample points that are far from each other. So that rather than, random sampling, it works great, but you sort of can, by just random chance, have a lot of, probability of sampling things that are very close to each other, whereas this actually has, sort of nicely dispersed samples that you get from this typically. And what that means is that it actually generally does a lot better than random uniform sampling in higher dimensions. But this is a practical thing, not a theoretical thing. In theory, it is still exponential in the dimension, as are all these techniques, really. It can also incorporate dynamics, so we're not going to talk about that today. But there are variants of RRTs that have dynamics. But one of the nicest things, really, is that this process of constructing the graph actually is really easy. It's just a tree. And we don't have to worry about kind of, do we connect this point or not in this graph? We just build a tree once, and it's just done. So very quickly, the way this works is the following. We start our tree at some point 0. And say this is our entire region. And remember, I'm drawing sort of a region now that's sort of a box. But this is really, think of this as the configuration space. We have this region, and now we sample a point randomly in this region. Say this point here. Actually, I guess first we add the initial vertex, which is the 0, 0 point here, to our tree. Then we sample a new point, a random new state in our configuration space. Check if it's non-colliding. If it's not colliding, we throw it out and keep doing that until we get a random state in our valids in the free space. Then we find the nearest neighbor to this point. In that case, the first case is easy. This just has to be this one, right? Otherwise, it'll be maybe something else in the tree. And we take a little step towards that point, where the step size in this case is epsilon. And we add this point to our tree. And we repeat. And just keep doing that. Randomly sample again. Say now we're here. Pick this nearest neighbor here and grow a little bit this way. This point here now, grow a little bit this way. We're not adding the random points we sample. What we're adding is the points that we grow a little bit towards, where we're growing a little bit towards those randomly sampled points. Now, if we sample a point that's actually within epsilon of our existing points, epsilon here isn't like machine precision. Epsilon here is like, you know, if this is like 1 and -1, a reasonable epsilon would be like 0.1. Something small enough, and actually that has to do with the size of obstacles in the space too. But don't worry about that. It's sort of something, you know, small, but not that small. If we're actually within epsilon of the point we sampled, then we just connect it, period. So if this is our point we sampled, then we'll just connect it exactly. But otherwise, we just keep growing in this process. And what's very cool here is that because we are sampling randomly, but we're more likely to sample areas where there's essentially, if we have big sort of areas with no tree in them, we are more likely to sample there than areas where we have sort of, that was imprecise what I was saying there. But basically, when we start off, there's a lot of empty space, right? And we're more likely to sample in that empty space than in the space we've already sampled before. So that means we're more likely to grow the tree outwards into the space where we haven't sampled yet. And this process kind of repeats, and actually is provable that this is getting, essentially, what it's doing is it's sampling, I think, weighted by the Voronoi diagram of all these points we have so far. So if you've seen that before, then that might make sense, but otherwise don't worry about it. But essentially what this means is that we are going to grow this tree very quickly into areas where we have not had any samples before. Now we can also do things like account for obstacles, but just not adding points if they are colliding. So if we are in fact going to collide, if there's an obstacle here, and we pick a point here, actually that would be fine because we're sort of still within epsilon. But if we pick a point inside the obstacle, well, we don't do that ever. So random state never says something within the obstacle. But then also, if we're here and pick a point here, and we would grow to within that obstacle, we don't allow that either. So if either x rand or x new is within an obstacle, we don't allow it. Again, you want to make sure that you're not taking steps that are going to go through an obstacle. So you actually want to have epsilon here be of that scale where epsilon is kind of small enough that you don't try to punch through obstacles here. But other than that, it's easy. You just don't allow things if x new or x rand is within an obstacle. And finally, there are lots of variants of this. So people also do things like forward-backward RRTs, where you have one RRT starting at the goal and one at the start state. That's nice because sometimes you have to do a lot less work. They will expand a lot less before they meet up than they would if you sort of started at one location and let it grow as only one tree. There are the dynamic versions, as I said, things that actually incorporate control and the dynamics of a system into this. There are also variants that essentially incorporate things like A-star search. So the RRT star algorithm is actually a pretty recent algorithm, I think 2010 or so, that more or less lets you change the parents of the tree to make, if you see a more efficient path, you actually take that more efficient path instead of the less efficient ones. So that is RRTs. And I guess I'll just let to show you how these look, what these look like, which everyone probably has seen this before if you've done RRTs before. But this is the kind of stuff they do. So basically what's happening here is we're starting right here, our RRT, and we're just growing. Epsilon, you can kind of actually even see how big it is. It's about this length right here. But very quickly, it starts to kind of branch out into the space as a whole and start filling up the space pretty densely. Yeah?
Using Voronoi diagrams?
No Voronoi diagrams at all. Just this procedure. So this is sort of the nice thing, right? So the RRTs are probabilistically actually doing the same thing as a Voronoi diagram would. But calculating a Voronoi diagram is very computationally intensive with respect to this thing. Here, literally, this is probably 10 lines of code. And that's just with actually, this one here is 5 lines. With optical check, it's a little bit more, but it's almost no code. And it's doing the exact same thing probabilistically as you would if you kind of do the very, very intelligent type sampling. You'll code it for the homework. So this is really, really simple. There's no geometry here at all. It is just select the state, really select the state, move towards that state, and that's it. And it does stuff like this. Here's now the example of when you have an obstacle, or many obstacles. So what's happening here is I am not letting it get anywhere within a small range around those obstacles here, but there's no sort of high dispersion sampling here. It's just random sampling, and it's covering this whole thing densely. It's just naturally sampling random points. There's sometimes over here and trying to grow over there, and so this is what it does. And if you look at it too, what you'll see is that the actual path you would take is something like this. Now, one thing about this, because this is a tree, here you're never changing the structure of the tree. So if you get a path to the goal, you'll never improve upon that path, right? Whereas a lot of subsequent work has actually been about how do you take these maybe as initial points, but then optimize them, because the paths you get from this are kind of very jerky, right? They're kind of these random paths through configuration space. It might not be actually what you want to do. But it's a really incredibly powerful algorithm. And again, as I said, it's probably about 5 or 10 lines of code that will do all this. OK, next time we'll talk about how do you actually incorporate dynamics here. Yeah, question?
Can you explain how this is less computationally expensive than random sampling?
So computationally, it's not as, it's fine. With random sampling, the problem is if you randomly sample this, that's fine. Now you have to actually build your graph. Uniform sampling. So this is using uniform sampling, so that's fine. The thing with uniform sampling is once you sample uniformly here, you have to also build your graph. And building your graph is a little bit nastier, right? You have to say, OK, which ones do I connect, which ones do I not connect? All the ones on here and then over here, maybe you have to say, OK, can I reach that one? Can I not reach that one? Every time you do this, you just find the nearest neighbor, which can be intensive too, but there's efficient ways of doing that. And then you just take a small step in one direction. So it can be very nice for that reason that you don't have to worry about any sort of building a graph on top of random samples. You just have a set of random samples. OK?